Okay, in this video we're going to talk about increasing and decreasing functions and how to tell whether a function is increasing or decreasing without having to look at the picture or the graph of it. We're going to be looking at the derivatives instead. Okay, on this first slide we've got our definitions in there. This is kind of a review, but in case you don't remember, basically what's going on here is the fact that we're saying that on the graph paper, if I pick an x value right here, and I pick another x value back here, and we can tell that x2 is bigger than x1 because it's further to the right, then the points that they correspond to, so let's just say that x1 corresponds to this value of y1 right here, and x2 might correspond to this value y2 up here, then we know that the function is going to be increasing because when x2 is bigger than x1, y2 is also bigger than y1, which we can tell because it's higher than y1 is on the y-axis here. So this is how we know something's increasing. Likewise for decreasing, if we pick our x1 down here and our x2 way over here, and let's just say x1 corresponds to a y1 way up here, and maybe x2 corresponds to a y2 down here. Now we know that y1 is greater than y2, or in this case y2 is less than y1, then we can say that this function is decreasing when x2 is bigger than x1, but y2 is smaller than y1, we know we've got it decreasing. And we can see the picture of it and know that it's going downhill and that it is in fact decreasing. And then right here we have the way that you might say it to somebody else rather than having the technical math definition for it. Here's our test for increasing and decreasing. We're going to assume that our function is actually differentiable on a particular interval, and it's an open interval. And we're going to be looking at the first derivative. And what we're going to be able to say is that if our first derivative is positive for every number that happens inside this interval, then we know it's increasing. And then in this one, if our first derivative is negative, because all numbers less than 0 are negatives, then we can say that our function is actually decreasing on the interval. And finally, if we know that our first derivative is equal to 0 for every number inside here, then we know it's constant. Now please know that there can be instances in the open interval where the derivative is 0, but it's not going to be every single one of them. It can happen for a finite number of places inside the interval, and that's okay. We can still have increasing, decreasing. If it's going to be constant, then everything in the interval has to be equal to 0. Okay, here's our first example. We need to show that the function f of x equals x to the fourth is decreasing on the open interval from negative infinity to 0, and then increasing on the open interval from 0 to positive infinity. Okay, so what we're going to be looking at, first of all, we need to take the first derivative of our function here. So we've got x to the fourth, that's going to give me 4 times x to the third power. Okay? Alright, now first of all, let's consider the interval going from negative infinity to 0. Okay? Now, without picking out any number in particular, we know that all of the numbers inside this interval are negative numbers, because anything to the left of 0 is going to be negative. And if we consider taking f prime of some negative number, we're going to have 4 times a negative number to the third power. Now, if I take a negative number and raise it to the third power, it's still going to be negative. So this guy is going to have to be some sort of a negative answer, regardless of what number I choose inside that interval there. And because of that, we know that on the interval here from negative infinity to 0, because the derivative is negative, this one is going to be decreasing, which is what we were trying to prove. Now we're going to use similar logic to show that it's increasing from 0 to infinity. Alright, so considering the interval from 0 to infinity, every number in here is positive because every number that's to the right of 0 is going to be positive. And if we look at the derivative of some positive number here, we're going to have 4 times a positive number raised to the third power. Now, it doesn't matter what that positive number is. When I multiply it by itself and then by itself again, I'm still going to have a positive answer, and then I'm going to multiply that by a positive 4, which means that all of this right here is going to be a positive number. And then, since my derivative results in a positive number regardless of what I pick over here in the interval, we can say that this one is going to be increasing, and this is going to be by the test for increasing and decreasing functions. Alright, let's look at example 2. From 2007 through 2012, the consumption B in pounds per person of blueberries in the United States can be modeled by B is equal to negative 0.01792 squared plus 0.485t minus 2.03, where 7 is less than or equal to t, which is less than or equal to 12, and t is equal to 7 corresponds to the year 2007. Show that the consumption of berries was increasing from 2007 to 2012. Alright, so basically what we're trying to do is show that this function is increasing on this interval right here from 7 to 12. And I know this should be a closed interval because we have the less than or equal to's, but your book is doing the increasing, decreasing thing on open intervals right now. So we'll talk later about how to get them increasing and decreasing on closed intervals. Okay. First thing we want to do is we need to know what the derivative is. Alright, b prime. Let's see. We're going to be multiplying 2 times negative 0.0179. This is going to be negative, and I have this written down, 0.0358 t plus 0.485, and then of course the derivative of 2.03 is going to be 0 right there. Okay, so here is our derivative. Okay, now we want to show that this thing is increasing, and that means that all of this right here has to be greater than 0, or greater than or equal to 0. And so one thing that we can do is we can take the derivative there and we can set this greater than 0, and what this will do is it'll tell me all the values of t that cause my derivative here to be a positive number. Alright, so let's subtract the 0.458 to the other side. This is going to leave me with negative 0.0358 t, still greater than negative 0.458. And then when we divide that negative 0.0358 out, don't forget to turn the sign around because we had to divide by a negative number. That means that t is actually going to be less than, and then when we do this division, y'all, it comes out to 13.547 and then a bunch of other decimals out there. But anyhow, as long as we have a number less than 13 and a half, then we know that this derivative is going to be positive. Okay, now remember our interval went from 7 to 12. And as long as my numbers are less than 13 and a half, this is going to be positive. So that means that it is increasing. Okay? On the interval from 7 to 12, because the upper limit on our interval 12 is less than the 13.547, which is all of the numbers that will keep us positive there. So we know that this is actually increasing on our interval. Okay, so here we have the definition for our critical numbers. We can say that if a function is defined as c is considered to be a critical number when we plug that into the first derivative and f prime of c is equal to 0, or we find out that f prime of c is actually undefined. Okay, here's how we can recognize our critical numbers. These are numbers where a continuous function might change sign, so it might go from the up above the x-axis down below the x-axis, or vice versa. And please note also that the critical numbers have to be in the domain of the original function f of x. Here's example 3. We're going to find the critical numbers of f of x is equal to x squared minus x. Well, remember, in order to be a critical number, we're trying to figure out where f prime of x is equal to 0, or where f prime of x is undefined. Alright, so what I'm going to do, first of all, is find the derivative of this thing. F prime of x is going to give me, let's see, the derivative of x squared is going to be 2x, and then the derivative of x is just 1. So here's my first derivative. Now, this, we know that if we drew the graph of it, this is just a line where the y-intercept's at -1 and the slope is 2, so it's not going to be undefined anywhere. This is a continuous function. But we can figure out where it's equal to 0. So I'm going to take my first derivative here, and I'm going to see what happens if I set it equal to 0. So what happens if 2x minus 1 is equal to 0? Well, we'll add 1 to the other side, and we'll get 2x equal to 1. And then when we divide by 2, we'll find out that x could be 1/2. So what this means is when I plug 1/2 into the first derivative, I'm going to get 0, which satisfies this requirement right here and makes x equals 1/2 a critical number. Here's the guidelines for applying the increasing and decreasing test. The first thing we want to do is find the derivative. Okay, then we want to locate those critical numbers, and that is, we're just going to figure out where the first derivative is 0 or where the first derivative is undefined. We're going to determine the sign of the first derivative at least one value in each of the intervals. So that means we're going to have something called test points. And then we're going to use that test for increasing and decreasing to decide if it's increasing or decreasing. So what's going to happen is, once we get here to step 3, we're going to pick at least one number from every interval that is created by these particular critical points, or critical numbers. And we're going to test one number from each interval into the first derivative there. And then if that number returns a positive value, then when we use the test for increasing and decreasing, we know that it's going to be increasing. And if it returns a negative value, then our test is going to tell us that the function is actually decreasing at that place. Okay? Alright, so let's go ahead and try one. Here we are at example 4. We're looking for the open intervals where f of x is equal to x to the third minus 12x is increasing or decreasing. Alright? The first thing we want to do is find that first derivative. F prime of x. The derivative of x to the third is 3x squared, and the derivative of 12x is going to be 12. This picture right here, if we were to draw it, it is a quadratic, so it's going to draw us a parabola, and we can say that it has a vertical stretch of 3, and that the y-intercept is going to be down here at -12. It's not in vertex form, so we can't tell by looking at it right here what the vertex is, but we do know that we have a y-intercept and that there is a vertical stretch going on. And we also know that it's opening up because the 3 is positive. But because we know the shape of this quadratic is going to be a parabola, we know that it's a continuous function, and so it's not going to be undefined anywhere. Alright, that means we're trying to figure out where f prime of x is going to be equal to 0, and we want to solve the equation 3x squared minus 12 is equal to 0. Okay, what I'm going to do is I'm going to actually add 12 to the other side here. We'll have 3x squared equal to 12, and now I can divide the 3 away, which leaves me with x squared is equal to 4. And now I'm going to unsquare this by using the square root. Don't forget to put in the plus or minus over here. The original problem didn't have a square root in it, so when you introduce the square root, you need to put in the plus minus. Okay, the radical and the power will cancel over here, and over here we're going to have positive or negative 2. Alright, these are the critical points. Now, we have to figure out what these actual intervals are. Now remember, all real numbers has the interval going from negative infinity to positive infinity. But the idea here is that our critical points are going to break apart the all real numbers interval into, I guess, subintervals or multiple intervals there. And so we're going to have to use negative 2 and positive 2 to break apart this interval right here. Now, if I were looking at this on a number line, this is all real numbers. Negative 2 is here, positive 2 is here. Now I'm going to put open circles on these because we're using open intervals. And we're trying to figure out these open intervals. Well, remember, the whole thing went from negative infinity to positive infinity. Now I've got my critical points involved. That means I have an interval here that goes from here to negative 2. I have an interval here that goes between these two, and I have an interval here that goes from there to there. And so my intervals, now I'm going to name them, go from negative infinity to negative 2, from negative 2 to positive 2, and then from positive 2 to positive infinity. So basically what we're doing is all real numbers except my critical points. And this is how we would write that down. Okay, now that we've actually identified the intervals, now we want to figure out whether my function is increasing or decreasing on each one of these intervals. So I'm going to erase all of this, and then I'm going to start using my checkpoints. Okay, so what I have here is I move my intervals up here so that you can actually see them up here above on the number line. And I'm going to pick some checkpoints. And remember, I have to pick one from each interval, which means I'm going to have one back here in the interval from negative infinity to negative 2. And then I'm going to need one in here from negative 2 to positive 2. And I'm going to need one here from 2 to positive infinity. And that's going to tell me for each interval whether my function is going to be increasing or decreasing. Okay, the idea here is that I only need to test one point, because back in 171 we had a theorem that said that if one of these is going to be positive, then everything in this interval is going to have to be positive as well. Likewise, if we test one point back here and it's negative, everything back here is going to be negative as well. So that makes it nice to only have to test one point. Okay, so I'm going to pick a point over here to the left of negative 2, and we can pick negative 3, but you can go crazy if you want to and pick negative 1,000. It really doesn't matter. Alright, so I'm going to check when x is equal to negative 3. And I'm going to plug it into my first derivative there. So we're going to have 3 times negative 3 squared minus 12. Alright, negative 3 times negative 3, that's 9. 9 times 3 is 27. So we're going to have 27 minus 12, which is going to give me 15. This is a positive number. And so that tells me that from negative infinity to negative 2, f of x is going to be increasing. Alright, now we're going to check something here in between negative 2 and positive 2. Now y'all, if 0 is inside an interval, it's almost always a good idea to use it as your checkpoint. And so 0 does fall in between negative 2 and positive 2, so I am going to use that here. And we're going to plug it into our function, to the first derivative there. We're going to have 3 times 0 squared minus 12. Well, 0 squared is 0 times 3 is 0, and 0 minus 12, that's just going to give me a negative 12. This is negative. And so by my increasing-decreasing test, if that first derivative is negative, that means everything in the interval from negative 2 to positive 2, we're going to be decreasing. The function's going to be decreasing. And then finally we need to check a point back here from 2 to positive infinity. And I'm just going to choose 3, but again, you can go crazy and choose 1000 if you want to. It doesn't matter, as long as it's the number to the right of positive 2. And we're going to plug it in. We're going to have f prime of positive 3. We'll have 3 times positive 3 squared minus 12. And then again, 3 squared is 9 times 3 is going to be 27 minus 12. This gives me 15, which is also a positive number. And that tells me that on the interval from 2 to positive infinity, my function is also increasing. Alright, so we found the first derivative. That was the first thing that we did. And then we had to figure out where those critical points were. That was step 2. And then once we found the critical points, we found the intervals right here. And then once we found those intervals, we used our test points to figure out if the function was increasing or decreasing in those different intervals there. Here we've got example 5. We're supposed to find the open intervals where f of x is equal to x to the power of 2/3 is increasing or decreasing. Now we have this one in here because this time we're going to have a situation where we actually have an undefined place, and we're using that as a critical point. So let's see what happens. The first thing we want to do is find the first derivative. So f prime of x is going to be 2/3 times x to the power of negative 1/3. And if we clean that up a little bit, it's going to be 2 over 3 times the cube root of x. And it would be the cube root of x to the power of 1, but we don't have to actually put that on there. So there's our first derivative. Okay, now we can't, f prime of x can't be equal to 0, because if we set that equal to 0, we're going to have 2 over the cube root of x equal to 0, and then if we do the cross multiplication thing, we're going to have 2 equal to 0, which can't happen. So it can't be equal to 0. And if we're going to have a critical point, then that means it has to be undefined somewhere. Well, we know that from our rules of domain. If you have a variable in the denominator, then there's going to be something excluded from the domain. Because if we have a variable in the denominator, we don't want the denominator to be equal to 0. So our next job is to find out, is our first derivative undefined somewhere? And the way to do that is we take the denominator 3 times the cube root of x, and we set it equal to 0, because remember, we don't want to divide by 0. Alright, if we divide that 3 away, we'll have the cube root of x equal to 0. And then to uncube root something, that means we need to raise both sides to the third power. So it should be an x. Alright, and then the power and the radical will cancel, so we're left with x, and then 0 to the third power is going to give me 0. And this is going to be my critical point, or my critical number. Now, if I'm picturing this on the number line, because I'm trying to get to my open intervals, remember the whole number line here goes from negative infinity to positive infinity, but we want to take the critical point out of that. So if we put 0 right here, notice that my number line has now been divided into 2 places. We have the left side of 0 and the right side of 0. So that means the interval to the left goes from negative infinity to 0, and then the interval on the right goes from 0 to positive infinity. So those are my two intervals where I want to decide whether my function is increasing or decreasing. Okay, so now we want to pick our test points. I need to pick something over here to the left of 0. Anything at all. I'm just going to choose positive 1. I'm sorry, I'm going to choose negative 1. Because negative 1 is to the left of 0, not positive 1. And we are going to plug that into our first derivative there. So we want to know, what is f prime of negative 1? Well, it's going to be 2 over 3 times the cube root of negative 1. Alright, well, the cube root of negative 1 is just negative 1. So we've got 2 over 3 times negative 1, which is going to give me negative 2/3. This is negative. And that tells me that from the interval negative infinity to 0, my function is decreasing. And now I'm going to test positive 1, because I want to test something over here to the right and find out if it's increasing or decreasing. And let's see, we're going to find f prime of positive 1. This is going to give me 2 over 3 times the cube root of positive 1. Well, the cube root of positive 1 is just 1, so we have 2 over 3 times 1, which is 2/3. This is a positive number. And that means on the interval from 0 to positive infinity, my function is going to be increasing.